Hi everyone. In this video, we are going to talk about the electromagnetic waves in free space. So the topic is EM waves in free space. So we will actually see how the Maxwell's equations transform in free space. That would be the first thing in this. Second, we'll try to get the wave equation in terms of E and B. So the main motivation for this topic would be writing the Maxwell's equations for free space. And second thing would be to derive the wave equation in terms of electric field and magnetic field. Since we know EM waves actually consist of electric field and magnetic field, and I don't need to mention here that electric field and magnetic field are perpendicular to each other and perpendicular to the propagation of wave. Okay, we'll do all these things, but let me tell you the assumptions. There are certain assumptions we take when we try to see the electromagnetic waves in free space. And the first assumption would be that the space is free from any bound or free charge. There are no bound charges, there are no free charges in the free space. Second thing would be there no bound currents and no free currents. That's both are zero. I would say J, it's J bound equals 0 and J free equals 0. These are the very two important assumptions. Bound charge is equal to 0, free charge equals 0, bound current equals 0, free current equals 0. Third is the space gets no polarization. No polarization happens to the space, no polarization, and no magnetization. A space doesn't get magnetized, neither it gets polarized. Okay. Fourth assumption is that the space is isotropic. When we say isotropic, we means all the properties are same in every direction. If there is some variation in some direction, so of some quantity, then the same quantity would vary in the different direction. We say the space is isotropic. No preferred directions. There are no direction which is more preferred than the other direction. X, Y, Z are same, in same preference. Okay. And the fifth one is space is homogeneous. Space is homogeneous. Every point is same. Again, no point is more preferable than the other point. So these are the assumptions for electromagnetic wave in free space. When we try to understand the electromagnetic waves, how is the behavior of EM waves in the free space. So these are the assumptions. And what are the fundamental things we try to understand in this chapter is that how the electric field and the magnetic field generate and sustain each other. Okay, that's the first motivation of this chapter. Not for this topic. For this topic, I have chosen these two things to understand. But for this chapter, electromagnetic waves in the free space, for the higher physics, what we try to understand how electric field and magnetic field generate and sustain each other. Second thing is that how electromagnetic waves propagate at the speed of light. I hopefully believe that you know one is C is root of mu 0 epsilon 0, how EM waves propagate at the speed of light. And we also try to study the structure and the direction of polarization of EM waves. Polarization of EM waves, not polarization of the material. Okay, we're going to understand the polarization of EM waves. So we try to see the linear polarization, circular polarization, and elliptical polarization. So we'll try to understand that well in this chapter. And what is the mainly what is the direction of polarization, and how transport of energy and momentum through fields actually exists. That's how does that happen. That is also the main motivation of this chapter, and the fundamental link between the light and the electromagnetism. So those are actually the main motives of this chapter. But for the video, first we'll try to understand how the Maxwell's equation, how they get transformed in the free space, or how we'll write the Maxwell's equation in the free space. Second thing, we'll try to understand the wave equation actually in terms of A and B. So let's go to the first part, this Maxwell's equation for free space. First one is Maxwell's equation in free space. And for that, let me write first the general Maxwell's equations. Del dot of E equals rho by epsilon 0. And second is del dot of B equals 0. Third is del cross of B equals minus dou B by dou T. Sorry. Del cross of E equals minus dou B by dou T. And fourth one is del cross of B equals mu 0 J plus mu 0 epsilon 0 dou E by dou T. So these are the differential forms of the Maxwell's equations, and there are accordingly the integral forms. In the last video, I have told how to transform the differential equation in the integral form by using the divergence theorem and the Stokes theorem. If you have not seen that video, just go and check that video, how we write the Maxwell's equations in the both differential form and in the integral form. So let's apply the assumptions. And let's see how they get transformed. First one, since the assumption is both row bound and the row free is equal to 0, so this row becomes 0. The first would become del dot of E equals 0. Second, del dot of B equals 0. Nothing happens to this equation, it remains as it is. Third, nothing happens to this equation. Del cross of E equals minus dou B by dou T. And since this J is 0, so fourth becomes del cross of B equals mu 0 epsilon 0 dou E by dou T. So this is the behavior of the Maxwell's equation in of electromagnetic waves in free space. Okay, so if somebody asks you in the examination, write the Maxwell's equation for electromagnetic waves in the free space, so these are those Maxwell's equations, because we need to apply the assumptions, and applying the assumptions we get all these equations. Now let's try to write the second motivation of this lecture. We'll try to understand the wave equation in terms of E and B. Okay, so first thing is that we know the general wave equation of classical wave. If we write the classical wave equation is del square f dou z square equals 1 over v square dou square f by dou t square. So f is actually in classical thing, it's f is actually the displacement. It's actually the displacement of particle. That string. If this is a string, so this is the displacement from the main position, this f. Okay, so obviously it's a function of time, and we believe that here the wave is propagating along z direction. So if we consider this as z direction, so wave is actually propagating in this direction, but the displacement is up and down. Okay, displacement is up and down. I hope you understand the SHM. Okay, actually particles of the string actually oscillate. So they do the SHM up and down while the wave is propagating along the z direction. Okay, so this is the wave equation. Wave equation. This is the general wave equation in string one. It's one dimension. So the wave is propagating along the z direction. So we also know from the very high school physics that this speed is actually tension in the string, and mu, where t is tension in the string and mu is mass per unit length of string. Okay, so that's the very important thing. Mu is the mass per unit length and t is the tension in the string. Now what we do here, the wave equation becomes in the electromagnetic waves, so this becomes like this. See how it gets transformed. Del square of E equals mu 0 epsilon 0 dou square E by dou t square, or in terms of B it becomes dou square B equals mu 0 epsilon 0 dou square B by dou t square. Okay, so actually in it is in three dimension. We can also write this equation in the 3 dimension or in the 2 dimensions. We can write it like this equation. We can write in the 2 dimensions dou square, let's say psi in place of f, dou square psi dou x square plus dou square psi and dou y square equals 1 over v square dou square psi dou square psi by dou t square. This would be in 2 dimension, and we can write accordingly in the 3 dimensions. We can write in the 3 dimensions dou square psi dou x square plus dou square psi dou y square plus dou square psi by dou z square equals 1 over v square dou square psi by dou t square. This is in the 3D. Now we'll derive this equation, these two equations. I'll try to derive both equations, and you'll understand how we actually get to these equations, and we'll also see this mu 0 epsilon 0 is actually, this v is root of 1 over root of mu 0 epsilon 0, or we know this is the speed of light 1 over mu 0 epsilon 0. In this it's the speed of wave. Okay, it's the speed of wave in the string, but we know here it's the speed of the electromagnetic wave, which is c, not the v. Okay, but you need to understand here that we'll always try to write in this way, because when we go to the chapter where electromagnetic waves in the dielectric material, then we'll take care this mu 0 and epsilon 0 will convert to something else. Okay, so let's try to prove the the wave equation. Actually, since we know the first equation, the Maxwell's equations, del cross of E equals minus dou B by dou T. This is the third Maxwell equation, and if we take curl on the both sides, curl of above equation, or we can take curl on the both sides, so del cross of E equals minus dou B by dou T del cross of B. Okay, now this is the famous del cross of E. If you don't know, it's equal to gradient of divergence of E minus del square of E. So there is a rule called the A cross B cross of C, that is equal to back minus cab. Okay, so you can refer here to the Griffith. He has given a bit details about this. Okay, but yeah, remember this is this. You can apply actually here, and it actually transforms this way. So finally it becomes this. So gradient of divergence of E minus the del square of E equals minus dou by dou T of del cross of B. If we know here del cross of B, this is mu 0 epsilon 0 dou E by dou T. So let's write it mu 0 epsilon 0 dou E by dou t, and this mu 0 epsilon 0, let's take it outside. But one more thing is del dot of E is 0. Del dot of E is 0, so this part is 0, so it's like gradient of 0 del square of E equals minus mu 0 epsilon 0 dou square E by dou t square. So this and this becomes dou square, so minus minus will go, which implies del square of E equals mu 0 epsilon 0 dou square E by dou t square. This is the first equation in terms of E. You can do exactly the same way. How? Let's say first what we did, we take curl of this equation. Now we'll take curl of this equation. If we see what we did, we took the third Maxwell's equation, and then took the curl on the both sides. Then took curl on the both sides, we actually do something, apply the Maxwell's equations. Now we'll take the fourth equation, del cross of B equals mu 0 epsilon 0 dou E by dou t. This is the fourth Maxwell's equation in the free space. Maxwell equation. Now we take curl on both sides. Curl of curl cross B. Okay. Equals mu 0 epsilon 0 dou by dou t of del cross of E. Is that okay? So exactly applying the same way, what it would become, gradient of del dot of B minus del square B equals mu 0 epsilon 0 dou by dou t of del cross of E. And we know del cross of E here, del cross of E is minus dou B by dou t. So let us write it like that, del dot of B minus del square B equals mu 0 epsilon 0 dou E by dou t. Del cross of E is minus dou B by dou t, applying the third Maxwell equation. And we know del dot of B is 0 because magnetic monopole does not exist. So this is this equation. So let's it becomes 0, so there remains minus del square B equals mu 0 epsilon 0. This, let's take this minus outside, so dou square B by dou t square, and minus minus will go, so del square B equals mu 0 epsilon 0 dou square B by dou t square. So this is the wave equation in terms of B. This is the wave equation in terms of B, and this mu 0 epsilon 0 is common here, you can check, and this mu 0 epsilon 0 can be written as we know speed of light is 1 over root of mu 0 epsilon 0, taking the root on the both sides, so c square equals 1 over mu 0 epsilon 0, which implies mu 0 epsilon 0 equals 1 over c square. So we can replace this by del square B equals 1 over c square dou square B by dou t square, and in the above equation del square E equals 1 over c square dou square E by dou t square. So these are the two wave equations in terms of E and B. I hopefully believe that you understand the mathematics. I didn't discuss any sort of physics here, but yes, certain assumptions I discussed, and then we applied the assumptions and we tried to write the Maxwell's equation in free space, and then we what we did, we took the third Maxwell's equation and take the curl on the both sides. We took this equation and take the curl on the both sides, then applied these things here. We did del dot of E equals 0, first one, and here what we did, we took del dot of B equals 0, and finally we came up with the wave equations. So thank you so much.